You touch a hot mug of coffee and recoil. The sun beats down on your skin, making you sweat. You sit by a fire, basking in warmth, and feel comforted. Heat seems obvious, something tangible that moves from one object to another. It's a force you can sense, a substance flowing from the fire to your hands or from the sun to your body. Everyday experience convinces us that heat is an entity, a mysterious thing that travels and surrounds us. But what if everything you thought you knew about heat is wrong? What if heat isn't something you can hold or pour, but a measure of something far more abstract? Humans have wrestled with this concept for centuries. Ancient philosophers imagined heat as a fluid caloric that flowed from hotter to colder objects. They believed in invisible currents, a kind of magical transfer, explaining why metals warmed in the sun or why water boiled over fire. Early scientists observed these effects and sought to quantify them, but the intuitive idea of heat as a thing persisted. For most of human history, heat was treated as a substance. We measured it, worried about it, and used it as a literal agent of change. Contrast this with what modern physics reveals. Heat is not a substance. It is energy in motion. The warmth you feel isn't a fluid entering your body. It's the result of molecules vibrating, colliding, and transferring kinetic energy. When your hands absorb warmth from a cup, the molecules in the cup are moving faster than the molecules in your skin. Energy flows from one set of molecules to another, not because heat is a thing, but because energy naturally distributes itself. This revelation changes how we interpret everyday experiences. That sunbeam warming your shoulder, that cozy fire, that steam rising from soup, they're not mysterious currents of heat. They are countless invisible particles in ceaseless motion. Heat is an emergent property of energy transfer at the molecular level. The next time you feel warmth or cold, you're witnessing a dance of atoms and molecules, a choreography dictated by energy itself, not some intangible fluid. Understanding this shifts your perspective. It challenges the way we think about cooking, weather, engines, and even the universe itself. The sensation of heat is just a hint of a deeper truth. Energy is always moving, always transferring, and what you feel is simply the result of countless microscopic interactions. And with that understanding, the foundation is laid to explore the true nature of heat, how it moves, how it behaves, and why it is nothing like you were taught in school. We often use heat and temperature interchangeably, as if they were the same thing. You say the soup is hot, the day is cold, or the engine is overheated. But this common language masks a profound truth. Temperature and heat are not the same. One measures an object's internal motion. The other measures the total energy contained in that motion. Confusing the two leads to misunderstandings, not just in everyday life, but in science itself. Imagine a bathtub filled with lukewarm water and a small cup of boiling water, which contains more heat. Intuitively, you might say the boiling cup, it's hotter after all. But that's misleading. The tub has far more water molecules in motion. The total energy, the heat content of the tub vastly exceeds the tiny cup, even though its temperature is lower. Heat is energy in transit, not a fixed property of an object. Temperature is merely an indicator of how fast molecules are vibrating on average. One is cumulative, the other is relative. Contrast this with what early scientists thought. Before the 19th century, the caloric theory treated heat as a substance that flowed from hotter to colder bodies, a weightless fluid invisible to the eye. This idea was elegant and simple. Heat flowed like water, could be stored, and could even leak from one object to another. But experiments, like James Joule's famous paddle wheel experiment, revealed cracks in this explanation. Joule measured how mechanical work converted into heat. He showed that energy could transform but never disappear. Heat wasn't a substance. It was motion, measurable in joules, not calories. Understanding the difference between heat and temperature unlocks insight into everything from weather patterns to engines. When a metal rod feels colder than water at the same temperature, it isn't actually colder. It simply conducts energy faster, pulling heat from your hand more efficiently. Ice melts not because it absorbs caloric substance, but because energy moves from the warmer environment into its rigid lattice, increasing molecular motion until the solid structure can no longer hold together. This distinction reframes your understanding of everyday phenomena. The warmth of a sunny day, the chill of a winter morning, the steam rising from your coffee, they are not objects themselves, not mysterious fluids, but expressions of energy in motion. Heat is the story of countless molecules transferring energy, colliding, vibrating, and redistributing kinetic energy across systems. Temperature is the way we perceive that story, a single number capturing the average speed of molecular dance. Recognizing this sets the stage to explore the invisible mechanisms behind energy transfer, the very engine of reality itself. Heat doesn't just sit still, it moves, and the way it moves defines much of the world we experience. Understanding the mechanisms of heat transfer is crucial because it reveals that hot and cold aren't intrinsic properties. They're relational, dependent on energy flowing between systems. There are three primary ways heat moves: conduction, convection, and radiation. Each has its own rules, its own logic, and its own surprises. Conduction is the transfer of energy through direct contact. Imagine touching a metal spoon that's been sitting in a hot pot. The heat doesn't teleport, it travels molecule by molecule. Vibrating atoms collide, passing kinetic energy along. Metals are excellent conductors because their electrons are free to move, acting like messengers carrying energy quickly across the lattice. In contrast, wood or plastic is a poor conductor. That's why a wooden spoon feels safe to touch, even if it's in the same pot. Conduction is intimate. It's the whispering of neighboring atoms, each nudging the next. Next is convection, the movement of heat through fluids, liquids, and gases. Heat makes matter move, warm air rises because it expands and becomes less dense, while cooler air sinks. The same principle governs boiling water. Heated molecules rise, cooler ones descend, creating circulation. Convection is a collective dance where energy transfer is combined with motion, creating currents visible in oceans, weather systems, and even the boiling of your coffee. It's the reason your room warms unevenly when heat radiates from a radiator, forming invisible patterns that subtly shape our environment. Finally, radiation transfers heat without any medium at all. Electromagnetic waves, especially infrared, carry energy across empty space. This is how the sun warms Earth across 93 million miles of vacuum. No molecules collide in space. The energy travels as waves, directly interacting with molecules when it reaches them. Radiation is different because it doesn't require a material to transmit energy. It's the universe's way of bridging gaps that conduction or convection cannot. These three mechanisms are interconnected. A pot on the stove uses conduction to heat its base, convection to circulate warmth through water, and radiation to emit heat into the surrounding air. Understanding them changes how you see the world. Warmth isn't a property you possess. It's energy constantly moving, interacting, and reshaping its environment. Heat in motion defines comfort, fuels engines, and drives natural phenomena. Recognizing this invisible flow brings clarity to questions you never realized were puzzling. Why does your hand burn on metal faster than wood? Why does hot air rise? Why does the Sunday feel warm despite the vacuum of space? The motion of heat isn't abstract. It's the pulse of the universe, a ceaseless transfer of energy dictating life, weather, and every physical process you take for granted. We instinctively equate heat with temperature. Touch a cup of coffee, and you say it's hot. Stand outside on a winter day, and the air feels cold. But this common assumption is misleading. Heat and temperature are related, but they are not the same thing. Understanding distinction is key to grasping why heat doesn't exist the way you think it does. Temperature is a measure of the average kinetic energy of particles in a substance. It tells you how fast, on average, molecules are moving. High temperature means molecules are jiggling vigorously. Low temperature means they move sluggishly. But temperature alone doesn't quantify the total energy a substance contains. That's where heat comes in. Heat is the transfer of energy between systems due to a temperature difference. A cup of coffee at 90 degrees Celsius has high temperature, but if it's a tiny espresso shot, it contains less total heat than a large pot of soup at 70 degrees Celsius. Heat depends not just on how fast molecules move, but also on how many molecules are moving. A small object can feel hotter, but hold less energy overall. This is why a small metal rod can burn your hand, while a bathtub of water at a lower temperature might not, even though it contains far more total energy. This distinction explains everyday paradoxes. Consider ice melting in a glass of water. The ice absorbs heat from the water, not because it's cold, but because energy moves from the warmer substance to the cooler one. During this process, the water's temperature drops while the ice melts. The energy transfer heat in motion is what drives the change, not the presence of inherent hotness or coldness. Another subtlety, thermal equilibrium. Heat moves until temperatures equalize, creating balance. Objects themselves don't store heat. They store energy. Heat is always in transit, never at rest. That's why calling something hot or cold can be misleading. It's the relative movement of energy that matters, not a static property of the object. Even our language misleads us. We say, I heated the soup, but technically we caused energy to flow into it. We cool a drink, meaning energy leaves it. Heat is the story of energy moving, and temperature is the snapshot of molecular motion at a given moment. By separating these concepts, the universe of energy becomes clearer. Warmth, cold, melting, boiling, and even the energy that powers engines and life are all expressions of energy in transit, not intrinsic qualities. Recognizing this distinction changes your perception of everyday reality. What you feel as heat is never a fixed property. It's the ongoing exchange of energy, a dynamic process that drives every physical phenomenon around you. Now that we understand heat is not a substance but a transfer of energy, we can see how this reshapes everything we thought we knew about energy in the world. Heat doesn't just warm your coffee or melt ice. It's the invisible thread connecting all physical processes. From engines to stars, from cooking to climate, consider a steam engine. The old explanation talks about hot water producing energy, but in reality, the engine operates because energy flows from the high temperature steam to the cooler surrounding surfaces, pushing pistons and moving machinery. It's the transfer of energy, not the heat itself, that does the work. The same principle applies to electricity generation. Car engines and even your microwave energy moving, interacting, transforming. Heat is never stored as a static entity. This perspective also reshapes how we think about the universe. Stars burn, planets orbit, and atmospheres circulate not because heat exists as a substance, but because energy flows from regions of higher to lower temperature, driving movement and change. When the sun warms Earth, photons transfer energy, causing molecules to move, winds to form, and oceans to churn. Heat is the messenger of energy, not a material you can bottle even at the microscopic scale. This insight matters. Chemical reactions in your body don't just produce heat. They transfer energy between molecules, altering bonds and motion. When you touch a hot pan, the sensation isn't because the pan has heat as a thing inside it. Your molecules absorb energy from the pan's faster moving molecules. The flow of energy, not some invisible substance, is what creates the experience of temperature. Understanding this distinction gives you clarity on everyday experiences too. Boiling water, cooling drinks, air conditioning, even walking barefoot on hot sand. All these events are interactions of energy, not a confrontation with heat itself. Once you see heat as motion and transfer rather than as a substance, your understanding of physics becomes more precise, intuitive, and connected to reality. This perspective also reframes scientific learning. Misconceptions like heat rises or objects contain heat crumble when we see that energy flows according to temperature differences, not inherent qualities. The universe is a network of moving energy constantly seeking balance, with temperature as a measure of molecular speed and heat as the dynamic bridge between regions. By rethinking heat, you not only correct a fundamental misunderstanding, but you also see energy itself in a new light, dynamic, flowing, and relational. Heat is not what you thought it was. It's a window into the motion of the universe, a principle that governs everything from your morning coffee to the life cycle of stars. Recognizing this transforms ordinary experience into a richer, more accurate understanding of the physical world.